hand sign.
I'm sorry?
The hand sign.
The hands. Oh, yeah.
You're very conservative in your use of the.
Oh, I thought I overdid it. Okay, I'm not a bell expert.
I don't really believe.
After it.
Right. Welcome back to the workshop. Today is all about lattices. We'll see, starting from Huck's talk, the progress on and open problems on the complexity of lattice problems, followed by a talk of Boaz Klartag on the KLS conjecture. And then we'll move on to algorithms in the afternoon and cryptography. So really, it's going to be a treat. Welcome. And
yeah, so thanks very much, Bennett, and thanks everyone for coming. So today I'll be talking about the complexity of lattice problems, my favorite topic, both giving a bit of a survey or just discussing the area in general, and also talking about a new hardness proof for the shortest vector problem. So I think it's natural that the clicker, or there's like a not good. So, what we'll be talking about is complexity of the approximate shortest vector problem, gap SVP, which is a computational problem on lattices. So as we all know, a lattice is the set of all integer linear combinations of some n linearly independent vectors. And usually this parameter n is what we use when we're thinking about measuring runtimes and approximation factors for lattice problems. So just as a reminder of what the LP norm of a vector is, I'll actually mostly just work in the Euclidean norm L2 and drop the subscript p, but occasionally I'll mention other norms. So a fundamental quantity associated with lattices is its minimum distance, the length of the shortest non-zero vector in the lattice. And the gamma approximate shortest vector problem is the problem in which you get a basis of a lattice and some distance threshold r is input. And the goal is to decide whether it's a yes instance where lambda1 is less than r, or a no instance where it's greater than gamma r. So in this picture here, this is what you see as input to SVP. So here's your basis. And your goal is to decide whether either all non-zero lattice points lie outside this circle, it's a no instance, or if there's some non-zero lattice point inside the blue circle, that's a yes instance. So here, if we look at the full lattice, we see that there are a couple of non-zero lattice points inside the blue circle. So this is a yes instance of gamma gap SVP. So again, I said this is a talk about complexity. So just kind of in a panoramic view, when you're thinking about the complexity of this problem, so this sort of slider, and Rajendra had a similar slide in his talk, where you can think of what happens to the complexity of this problem as we vary the approximation factor, which we think of as depending on n. So just at a panoramic level, you should think of exponential approximation factors being easy, constant approximation factors being hard, and sort of in the middle, we have crypto. And what I mean by that is we don't really know, or we don't have like, can't show as strong of hardness for these, but assuming that SVP is hard for some sufficiently large polynomial approximation factor, in the worst case, we get provable hardness of lattice crypto. So let me zoom in on that and just kind of look at this in more detail. So starting with the work of LLL and working forward, we actually show that, have shown that SVP with a slightly sub-exponential approximation factor is in P. So we have that if n approximate SVP is hard in the worst case, then SIS, which is an average case problem, is provably hard. And something similar holds for if we take gamma to be n to the 3/2 for LWE. So if we can prove that that gap SVP is hard to within these factors in the worst case, then we get that lattice crypto is provably secure.
What's SIS again?
This is short integer solutions problem. So yeah, it's like something, it's actually, so you get like most like mini crypt primitives from SIS, whereas you get like cryptomania and more from LWE. Yeah. Right. So unfortunately, there are barriers to showing NP hardness of these problems, as shown in a couple of results around 2000. So we have these results here where we actually have reason to believe that that SVP with polynomial approximation factors or any approximation factors greater than this are not NP hard. So if we showed that n approximate SVP is NP hard, then the polynomial hierarchy would collapse, which we don't think is likely to happen. And then the focus of this talk, what I like to think about a lot is sort of the hard regime, when we do have provable hardness under standard complexity assumptions. So this sort of got kicked off in the 90s when ITI showed that exact SVP is NP hard. And then if you're willing to make a stronger hardness assumption of some sort, either some variant of ETH or that NP is not contained, say, in sub-exponential time, then you get better fine-grained hardness or better hardness of approximation. So we have like exponential hardness for near exact SVP, and then for if you make a stronger hardness assumption, then we get stronger hardness for near polynomial approximate SVP.
Just to understand, stacking rectangle from the left. Co-NP. So non-existence of a short vector in NP. Is that what's meant by?
Well, square root approximate, yeah. So we can't certify that there's no vector within distance, say, yeah. So we can, yeah, certify either, or say, yeah, so we can't certify it exactly, like exactly what the distance of a shortest non-zero vector is, or length of a shortest non-zero vector is, but we can do it for this like approximate version of the problem.
So is it just stated that it's in NP?
So it's in NP for all approximation factors. So
You just produce the vector.
yeah, just the witness is like a non-zero
So the
vector.
real result for the hardness barrier rectangle is that this stuff is in both NP and co-NP.
Yeah, definitely. Or I mean co-AM in this case, but same.
So then you can't. So then life is nuts if anything like that is NP complete, because NP is
exactly. So that's why they're called hardness barriers. So we'd love to show hardness of SVP with these approximation factors, but we don't think we can because it would imply like complexity.
Now I understand what you're saying by that one.
Does that make sense?
Yes.
Now, okay.
Absolutely.
Yeah.
Okay.
Is there any other problem in complexity with like this many qualitatively different behaviors?
And well, it's like, so no, but I mean, if you want to study complexity theory, just study lattice problems. And believe it or not, even though this has a lot of stuff on it, there's actually even more to be said about this. So, I'd love to talk in even more detail, like about this, but like this is even just sort of the greatest hits in my opinion for.
So quick question: if you use other types of, I guess you'll talk about other norms, but things like LPN, will this be covered also by your talk? Like how the landscape changes if you look at the coding theory style norms? Will this be covered in the rest of
I didn't quite. It sounds very close, but I didn't quite catch what
So
you.
if you look at the coding theory style of noise, right? So lattices, you can think of it as having a linear code and then having some distribution over noise, which in lattices is something specific. And then there is the alternative coding theory.
So you just want to, there are a couple of things going on there, but I mean, for noise, you can think of it as like worst case noise, though, not average case.
Bounded humming.
Humming noise.
Well, that's not noise though, but like that's the metric. So you can think of it in terms of the Hamming metric. No, but I mean, really the kind of the key difference between codes and lattices is that we're thinking in terms of LP norms instead of Hamming norms. But codes will play a key role in what I say.
But my question is about this landscape. If you look at codes, I mean, maybe it's not in scope, but
no, it's a really good question. So so codes, actually a lot of things are analogous between codes and lattices, and we actually do know more. I think maybe let me just make a remark and then I'll come back to that, and just because you brought it up, which is a really good point. So this will keep that in mind. So, but sort of a key point here to observe, something that'll be the focus of this talk, is that all of these hardness results, everything in this left rectangle here, all of these hardness results are under randomized complexity assumptions. So in particular, we only know hardness for exact SVP under randomized reductions. We don't even know that exact SVP is NP hard under deterministic reductions. And this is something that came up on the complexity blog just earlier this week. So people are very surprised by this. This is like the hallmark problem. SVP is the hallmark problem in lattices, and yet we can't even show that exact SVP is hard. So back to the question, for codes, the situation is different. We know that the analogous problem to the shortest vector problem on codes is NP hard under a deterministic reduction, and that's actually due to Cheng and Wan. So, and that was actually relatively recently shown, I mean, within the last 10 years, I think. So,
What was the?
No,
What did you just say? Which things?
just the minimum distance problem, which is the analog of the shortest vector problem on codes, is known to be NP hard under deterministic reductions. So, under reductions under the standard notion.
There is a similar picture that you can draw for the learning parity with noise. So hardness of decoding.
Is there? I mean, is there worst case? Are there like worst case to average case reductions for LPN?
There are two
Yeah.
things that are missing. One is there is no worst case to average case reduction.
And
Up to, well, I mean, that's.
Yeah.
entirely
Worst
true.
case to average case reduction.
Sorry,
You have a worst case to average.
I know
case
that's not
reduction.
entirely true, but
Yeah.
that's not.
oh, that sounds cool. I want to hear about it anyway. Yeah.
And there are no sort of these hardness barriers.
Right,
I
right,
think
right.
That's not true, but up to a.
Yeah, no, it's interesting. So it's funny. I was talking to people like a week ago or so, like Venkat, about whether actually we could adapt some of the techniques, say, from lattices and port them to codes, but it's not. I thought about it a bit. It's not. I don't think it's written down. It's not clear that you get anything really.
So
by doing that.
The thing that Noah's talking about is the Rasamil Badim and Zika and Daniel. That says if that's a reduction from an easy coding problem to a hard coding problem. That sounds like the wrong thing.
Yeah,
to do.
yeah.
But it's an easy worst case coding.
Oh, got
problem
it,
to
to
a
it.
hard average case coding problem. So there's something.
Yeah. No, that's very nice. I mean, yeah. I mean, some of the crypto systems based on LPN look very similar to ones based on LWE and like the hard, I don't know. So what you need for, yeah, I don't know. Anyway, I think they're very nice. Just like the takeaway message here is there are a lot of analogs between codes and lattices, and it's really interesting to think about these complexity questions for codes.
Can you say again why it's a problem that the reductions are randomized?
Well, I mean, it depends on who you ask. I mean, for some people, well, it's not, but you
Yeah,
know,
no,
I mean,
but that doesn't prevent you from doing something with the problem. that you-
in crypto, not really, no.
Right,
But
yeah.
I mean, it's like, you know, why do we care about de-randomization in
Yeah,
general?
fine,
It's like we
fine,
feel
okay.
like we don't understand a
Yeah.
problem.
All right, got
completely.
it.
So,
Thanks.
Scott, given standard de-randomization assumptions, this can be.
Right, yeah, sure. I mean,
I
I
don't-
was just
yeah.
wondering if there was
But-
some, result that, you would only follow from a deterministic reduction, but all right, thanks.
no, I don't think there's
Thank
any,
you.
yeah,
Thank
but
I think the point is, it's not a problem, it's a disclaimer.
well, it's, I mean, it
Which
depends,
is
I don't know.
something that, you know,
Fine,
we all
yeah.
do this.
Yeah,
I mean,
I understand.
No, I'm not surprised. I was wondering if it would be, you know, so there's this philosophical question, how much should we care about randomness or something? But, you know, like primes and P is a big result. People really, you know, in practice, like you just run your BPP algorithm for primality testing, you know, a few times and, you know, everything works, but for applications, but
For the LWE business, at first, there was the disclaimer, I'm not sure if it's still true, but at the beginning, there was the disclaimer that it was a quantum reduction.
still, yeah, I mean, there are classical reductions known now, but I guess not with as strong of parameters. As
Right,
as
so-
original
so-
quantum reduction.
Problem, I don't know, but we're used to this as a type of disclaimer, that's all.
So you're saying, is there still a range here where we only have quantum reductions or?
I don't know about, that's a good question. I don't know about the approximation factor, but there are other parameters for LWE, like the modulus that you care about. And
I
I don't, somebody else knows all the trade-offs between stuff better than I do, but yeah.
All right, thanks.
Same approximation factor. So, but there is a qualitative difference that is that the quantum reduction is still better. In the sense that quantum reduction can actually solve a search problem given LWE solver. We're not able to do that with the classical reduction. And we don't know how to relate search and decision, you know, in this approximation.
Convention also square, like you switch from the exponential Q down to polynomial.
Possibly, yeah. Possibly there are other sort of issues as well.
This is a great discussion, but I'm also interested in the rest of Huck.
I appreciate that. No, but I mean, I kind of had it in mind. Like one thing I love about Simon's talks is there's often great discussion just because there's so much engagement. But yeah, let me get a little farther, but it's great. Like honestly, I'd rather just kind of present the survey stuff and have people talk about it. Then you can ask me more questions offline if you want. Right. So just in summary, so here's just the cutting to the chase about what we did. So actually, I'll first say what we tried to do. So Chris Piker and I spent a lot of time trying to prove deterministic NP hardness of SVP. So this is actually a problem that I think Daniele Machancho is kind of the world expert on this and has like put a lot of effort into it. We started with a lot of what he'd done and what other people had done, what Cheng and Wan had done for MVP and tried to adapt it. So unfortunately, we didn't succeed with this, but my joke of I have to explain it. So yeah, that's never works well. So what did we do? So we gave what to me, I think is the simplest randomized NP hardness reduction for SVP. And kind of the key new ingredient for this was gadget lattices built from Reed-Solomon codes. We also gave concrete approaches for de-randomizing the reduction. So like even though we didn't succeed, we have concrete ideas about how to go about it that I hope some of you will take a look at and maybe succeed with. And then we also studied applications and connections of our work with other areas, particularly to decoding. So just kind of as a fun aside, so it's actually, we have good algorithms for decoding from our family of lattices, although with slightly different parameters than we use in our hardness reduction. And then our work also gives an approach for improved list decoding lower bounds for Reed-Solomon codes, where here I mean list decoding lower bounds in the standard Hamming sense. So we have some cool applications and connections to other areas. So whatever else I get to, this is sort of the punchline of what we tried to do, the sort of the problem we were trying to solve, and then what we did do. So we'll spend some time now going through what I call the Itai-Machancho approach for proving NP hardness of SVP. Was there a question? No. Okay. So as with any hardness reduction, we need to pick a starting hard problem. So in this case, to reduce from. So in this case, the starting hard problem is a variant of the closest vector problem. So to define this, I just need one piece of notation, which is just the distance of a vector t from a lattice. Right. So gap CVP prime is the variant of CVP where we have stronger promises both in the yes and no case. So in the yes case, we're promised not just that the target is close to the lattice, but that it's close to a binary combination of basis vectors. And in the no case, we're not just promised that the target is far from the lattice, but we're promised that all non-zero integer multiples of the target are far from the lattice. And Aurora et al. Proved that this problem is NP hard to approximate within any constant in the Lagrange. This is our starting hard problem. Okay, so step 2 is Canon's embedding. So basically, sort of what's maybe the first thing you'd think of when trying to reduce CVP to SVP? So, it's basically this. So we basically just pretend that the target vector is just like another basis vector. So just append the target vector, or say minus the target vector, as another vector in the basis, and then I just add some orthogonal component. But don't worry about that too much. Just in case it helps anyone, this is basically the same thing you're doing as like a primal attack on LW. Just like the target. And then, so if we want to analyze this reduction, so I'm omitting R and say R prime, the distance thresholds. But if we just want to think of this as a reduction from CVP to SVP, I'm going to do this by analyzing vectors in the lattice generated by B prime in terms of their coefficient vectors X prime. So in the yes to yes case, so assuming that there was in fact a short vector in the lattice generated by B to T, there's a short non-zero vector in the lattice generated by B prime. So this is not too hard to see. So so we just take the coefficients of the close vector there, and we just, for our new coefficient vector, we just take that X and then just append a 1 to it. So just qualitatively, then the distance between the X and T we already are assuming is small, and so here we have a short non-zero vector in lattice generated by B. So for the no to no analysis, now we want to show that for all non-zero X prime, all coefficient vector non-zero coefficient vectors X prime, B prime X prime is large. So just based on our promise from gap CVP, if Y is non-zero, this just kind of follows immediately. But then there's this problem when Y is 0. So in other words, when B prime X prime is really just BX, which is a vector in the original. So we're just ignoring this last column. And whether this is large or not depends on the minimum distance of the lattice and the input. So this reduction will work.
Can you say what's the point of this this last?
This term? Yeah, so I'm like intentionally annoyed. It doesn't play a large role in it. You need to set U appropriately, but everything kind of just works. So
Can I set it to be 0?
no, but I mean, just for actually, okay. So actually, sometimes you do set it to be 0, like if these are like embedded in some like higher dimensional space. That actually is how a lot of reductions work. But you need, I mean, you need this last column to be linearly independent. So that's, yeah, it's the main. I mean, you need to set U appropriately, but it's not the interesting part of it. So I'm not analyzing that at all. It's true, but it's just you. I mean, the reduction works for that. You don't look convinced, but yeah.
If there isn't a good reason for it to be there, why?
Well, I mean, you need linear independence. That's why.
That's it.
Yeah. So just think of it that. I mean, yeah. Yeah. So, great. Yeah. So in this case, like I was saying, this quantity depends on the minimum distance of the original lattice, which, you know, this reduction would work basically if and only if the minimum distance of the original lattice happens to be large. We don't know in general with it whether it is. So this is kind of the entire problem with the approach shown in this slide. Why we have trouble showing hardness of SVP.
Can you treat the anti-hardness of the CVP prime? Right, so that's a reduction from some other anti-hard problem like set cover.
Exact cover, yeah, is what they
So
did.
tweak it so that can you tweak it so that the resulting lattice actually has large lambda 1?
I'm not sure what you get like direct. I mean, I don't think that just works. I need to think. Yeah, you got like, I mean, like the lattices are like some instance matrix, set cover instance or something, but I don't see how you can just, yeah, get that. Obviously.
But in general, sort of the template is, modify the, make the gap CVP prime promise stronger, so this becomes actually not a problem at all.
Yeah, no, that's true, and I mean, so yeah, it's an interesting approach. So you like sort of just take the issue like downstream or whatever, or upstream.
Okay.
Anyway, and yeah, try to show like that like some easier version or even more restricted version of CVP is in fact hard, and then just introduction. It's an interesting approach. I'm not sure how to do that, but yeah. So so kind of the standard approach, the Itai-Machancho approach, is to do something a bit different, which is like we kind of want to force, this is how you should think about it, the minimum distance of lattice generated by B to be large. And the way we're going to do that is using geometric objects called locally dense lattices. So what's a locally dense lattice? So just intuitively, it's a lattice and a target pair such that there are no short vector, non-zero vectors in the lattice, and a whole bunch of close vectors, where by close, I mean at distance alpha times lambda 1 to the target. For some constants, missing a t, yeah, for some constant alpha between a half and strictly less than 1. Any such alpha is good enough in this range is good enough to make this reduction work. So alpha being smaller is better. Alpha can't be less than a half just by the triangle inequality. So like if you have two lattice vectors which are at distance 0.6 lambda 1 to your target, each at 0.3 distance 0.3 lambda 1 to your target, then the distance between them is at most 0.6 lambda 1. Right, so just here's like an example. Just everything works very nicely just with the integer lattice. If we're thinking just in 2 dimensions, of course, the challenge, with finding these lattices, we'll see how they come up in the reduction in a second, is in larger dimensions. So here, just we look at corners of the unit square. So we put a target in the middle, and then we have 4 vectors at distance 1 over square root of 2, which is 1 over square root of 2 times the minimum distance. So basically what Itai and Machancho showed, and later Lubachevsky and Machancho showed for BDD, is that if you construct one of these gadgets for a given alpha, then you immediately get 1 over alpha hardness of gap SVP and hardness of 1 over alpha gap SVP and of alpha BDD. Okay, so like you construct one of these gadgets, or a family of these gadgets with a smaller alpha, then you've shown stronger hardness for lattice problems. So these are also interesting geometric objects in their own right. They're connected to efficient decoding on lattices and various other things. Right. So one key point here is that we have a hard time constructing these gadgets deterministically. So in fact, the key use of randomness in hardness reductions is in constructing these gadget lattices. Okay, so say we nevertheless have one of these in hand. Like, how can we use it to help with our reduction from CVP to SVP? So basically, we just tack it on underneath our original basis, and we do the same thing with the corresponding targets, maybe with some scaling factor beta, whatever. Right? Kind of the idea now is that so again, the intuition here is that the lattice generated by A has no short vectors, so lambda1 is large. So this makes lambda1 of this whole thing. You think of these two, this stack as corresponding to B in the previous slide. You know that lambda1 of that is now large. Okay. And nevertheless, we still have lots of close vectors. Some co-set of the lattice generated by. So let's just kind of look at this in the idealized world in the L infinity norm. So here we can basically just take our lattice, our gadget lattice, to be Zn, and we take the target just to be the all haps vector. So I scale that a little bit when I'm plugging it in here, but if you stare at this a bit, you'll see that this reduction here actually just works. This is a full reduction showing hardness of deterministic NP hardness of gap SVP in the L infinity norm. Okay.
Does it actually show even more hardness approximation?
Yeah, well, depending on the approximation factor. Yeah, but if we reduce from, I don't know, you probably get like, I don't know if, yeah, 2, exactly. So, but you should observe that there's something special going on here. So this reduction worked because there's a correspondence between close vectors in our locally dense lattice here and potential close vectors in the original lattice in terms of the correspondence with their coefficient vectors x. Okay. So kind of the last remaining issue in this reduction is, in general, this won't be true for a locally dense lattice, and you need some way of establishing a correspondence between close vectors in the lattice generated by A and lattice generated by B. So this is actually not super interesting for the purposes of this talk, but I just want you to be aware of it. Another kind of just one thing that is worth noting is this is another place where randomness is typically used in reduction. dimensions. So kind of the main spot is in just constructing locally dense lattices, but we also need it using current techniques for generating a math T between close. All right, great. So
again, what does the map need to do?
yeah, well, there are variants of it. The easiest way to state it, which is actually not what we do exactly, but you just map from coefficient vectors, which you say take to be binary, of close vectors in elevate to S onto all possible coefficient vectors of close vectors in this lattice, so that you want like the entire hypercube 0, 1 to the n to be contained in the image of T. And then you stick T like here.
So, if the linear map is random and the set of close vectors is large enough, you expect to hit the entire.
Yeah, you're like kind of hashing down some like large set of vectors in some higher dimension down to like some lower dimensional space. But this, you lose a lot in terms of parameters like, you know, the rank blow up you need and stuff like that's where, yeah. So anyway, it's an interesting question whether this can be done better, but sort of not the step that's the focus here. Cool. So, right. So now we're all experts in reducing CVP to SVP. So, but there's the question of kind of like, you know, what's the story for these gadgets? Like this reduction works assuming that we have these gadgets, but you know, do they actually exist? And if so, what do they look like? So I have here like a summary slide about constructions of locally dense lattices, not just in the L2 norm, but actually in general LP norms. So the original work showing hardness of SVP constructed these locally dense lattices from, I guess, the Schnorr-Edelman prime number lattices. And so you get some nice approximation factor. So this is optimal for what it's worth in both L1 and L2. You can't have smaller alpha. And Daniele in his awesome 2001 paper sort of showed that you can actually de-randomize this reduction under like a strong number theoretic conjecture, which seems to be out of reach. Follow-up work constructed locally dense lattices from error correcting codes, specifically BCH codes, and these had the sort of nice property that the resulting lattices you get from doing this, from using these types of locally dense lattices tensor nicely, meaning that sort of if you tensor like a lattice with itself, then the minimum distance squares. And so because of this let us show, or let Daniele and Subhash and others show strong hardness of approximation results for more recently, some really cool work, like beautiful work by Devesh and Noah, started looking at showing fine-grained hardness results for SVP. And sort of the key here for fine-grained hardness is having like exponentially many, not just sub-exponentially many close vectors. And so they were able to construct locally dense lattices in this way by using sparsified ZN and from so-called exponential kissing number lattices with exponentially many shortest vectors. And then we in a couple of other works with Pikert and Tang kind of refined this analysis and ported it to show hardness results for bounded distance. So the focus of this talk is to talk about another construction based on codes, which I think is the simplest of all of these, maybe, which is to use lattices constructed from Reed-Solomon codes. So it's simple and hopefully, like even more importantly, hopefully de-randomizable. Okay.
Can you sort of maybe briefly say what's the source of randomness in these these other reductions. The prime number lattice, right? I mean, is the conjecture that there are enough prime numbers in small intervals?
It's not about prime numbers, it's about like smooth numbers and intervals. So yeah, smooth numbers wind up being what you need to construct like the target. And so if you have like, you know, sufficiently smooth numbers and sufficiently small intervals, or all sufficiently small intervals, then you can just like iterate through the interval and just find a point. Yeah. So yeah, there are differences in where you need the randomness in these. So generally, so you know, we want to construct like a lattice target pair for our locally dense lattice. Most of these constructions use the randomness to sample the target, but actually, like, there's an interesting point where with this sparsified ZN, actually using the randomness, they have like a fixed target, and then they're actually just taking some random sublattice of ZN. So in that case, you're using the randomness to construct the lattice, not the target.
So are these the same assumptions you need for the analysis of the number field set and their density of smooth?
Oh, I'm not sure
Okay.
that they're kind of, yeah.
Sounded familiar.
No, I'm sure somebody would know that better than I. Yeah, I'm not sure.
Oh, okay. Thanks, Nandi.
Yeah, no, that sounds very interesting. You mean for the,
Yeah.
yeah. Yeah, cool.
I think it's for the other constructions. Sparsification means sort of imposing a random linear constraint on the lattice, right?
Yeah, exactly.
So
That's what's done here. So yeah, I mean, I'm hiding, like, there's a separate reduction that Subhash uses, like, which uses sparsification just as like a primary thing. But yeah, so I'm hiding that detail here, but that's another place where randomness gets used in his reduction. So yeah, with his reduction, you actually have two-sided error. With the Itai-Machancho reduction, you only have one-sided error. Cool. So, right. So let me tell you about our locally dense lattice construction, the sort of last line of the table. So to do this, you need a little bit of notation, but hopefully not too bad. So just fix Q to be a prime and let K be some small polynomial in Q, like you can think of K as like Q to the 0.01 or something. And then I'm going to define just the following matrix, this van der Waals matrix. So you don't have to know what a parity check matrix is, although it'll be clear from the next definition, but just this is some matrix. Okay, so I just have 0th powers of the numbers from 0 to Q minus 1, mod Q in the first row, first powers in the second row, and so on. Okay. And from this this matrix, we can define a corresponding parity check lattice. So it's just the set of all vectors, integer vectors x, such that hx mod q is equal to the 0 vector. So yeah, this should look familiar. This is like the type of lattices or the construction used for constructing lattices in SIS. Just there, you're taking some random matrix A instead of this particular. Right. So for those familiar with it, it turns out that this is the parity check matrix of a particular Reed-Solomon code. So particular, like one with over FQ with evaluation set FQ and of dimension Q minus K. So I'm the coding theorist might be upset, but I'm using K here to mean codimension, not dimension. Yeah, this is the construction A lattice.
We're gonna have to talk.
Have you?
Yeah.
I'd be very curious to hear about that. So
Not for anything like this, but yeah.
well, I mean, yeah, but that's awesome. Yeah, it turned out that Daniele and Nadia had actually thought about using these lattices like a while ago for another application too. I guess not for hardness.
I used them for packing, well, very similar lattices for packing polyominoes.
I mean, that might be I mean, there's some sort of density thing which comes up maybe as a local density. Yeah, so they're also dense in the standard sense. Anyway, so So these are our locally dense lattices, right? But to have a locally dense lattice, we don't just need a lattice, we also need a target vector, which are equivalently a coset of the lattice with many short. Right. So this will be the most technical slide in the talk, but hopefully it's not too bad. So this is basically, if you just believe me on a couple of things, this will be like the full randomized construction of locally dense lattices in this slide. So the key is just to start with is to analyze the parameters of these lattices. So the Hamming minimum distance of this code is k+1. Okay, but kind of the secret sauce, which makes everything work, and like the super cool thing is that the L1 minimum distance of these codes is actually almost twice as large. So that's the key that really makes everything work. So you can define L1 distance natively on codes. It actually has a name. It's called Lie distance, but that actually doesn't matter here. It's just like it's equivalent just to the L1. So I'm using this superscript 1 to denote the L1 minimum distance of the corresponding lattice. Okay, and so we actually originally adapted a proof of this that Conway and Sloan used for a close but not identical family of lattices. But then it turned out actually that people had thought of this actually for this exact family of lattices, or I guess showing Lie distance lower bounds for these codes a while earlier. So I don't want to talk about this now. I mean, but it's like not a hard proof. It's nice. Works via Newton's identities. So the second thing, which is just the determinant of this code. So for integer lattices, the determinant is just its number of integer cosets, or equivalently, just the size of this quotient group, which here is q to the k. Okay, so we have minimum distance at least 2k, and we have determinant q to the k. Yeah.
Right answer is 2k.
Yes, in general. So maybe so we have like, I mean, this was also already known, or at least something very close to it was, but
What do you mean by in general? I mean, everything is here is fixed.
no, I mean, it depends on like what you pick Q and K to be. So
there's a choice of Q and K.
Yeah, and that sometimes it's tight. Yeah, it would actually imply something too strong, I guess, if it were in general. I need to think, because you would get like locally dense lattices that were too good. So yeah.
But for the purpose of the reduction, Q and K are up to you, or at least Q is
Yeah, you can pick, and we can officially construct like these lattices and stuff. You can take Q and K to be whatever you want. So here I'm taking Q to be prime, not just a prime power, but right.
This actually has applications in crypto. The L1 thing where you can construct a multiset from a power sum, right?
That's very much how this proof works. Actually, is something very close to that. Yeah. That's awesome. So maybe it's connected to other stuff.
I suppose there you need efficient decoding, probably, right?
Yeah.
Yeah.
Well, yeah, there's an interesting point where Roth and Siegel actually showed efficient decoding in Lie distance, or in L1, say from the corresponding lattices. We show like efficient decoding in L2 that's better than what is implied by a bit of a sign. Okay, so cool. So we understand the two fundamental parameters of our lattices. So you just need one definition, which is just the weight H slice of the Hamming cube. So which I'm going to use this notation. Okay, and so our goal here, like what we're going to do, let's just think about how we would construct locally dense lattices here using these lattices in L1. So what we're going to do is we're going to find some S such that the coset L minus S contains many vectors in BQH. So for this to work, to get alpha local density, we need to take have H parameterized in this way. We need H to be less than alpha lambda 1. So let's set it equal to alpha times 2k. And then like just sort of we get what we need just from, in an existential sense, just from like a pigeonhole argument. So in particular, we get that so there are q to the h many vectors in this set, and there are q to the k cosets in the lattice, and so some coset has to contain at least q to the 2 alpha minus 1 times k vectors in BQH, which if alpha is greater than a half, this number is greater than 0. And just if you remember, so this q to the epsilon is coming from how I originally set k, which to be q to the epsilon. Okay, and so that's what we needed, right? Because this quantity is sub-exponentially large.
So the larger the H is actually the better for this.
You get more vectors, but you show worse local density. So like there's kind of this trade-off, yeah, between the two. So you get more close vectors, but like you're, yeah, kind of you get a worse locally dense lattice in terms of alpha. Right. And it's not hard to get a randomized version of this. You just do kind of like the most basic thing that you'd imagine. You just sample a random S from BQH. I guess the one thing to note is it's not enough just to sample like a vector from just like from a uniformly random coset. It has to be one from but yeah.
Can I recognize if I've succeeded? Can I sample?
I don't see how you can, but yeah, it's a good question.
Yeah, I don't know, resolve it.
Yeah, that's it.
Yeah, there'd be a way.
Yeah.
But yeah, I don't know. It's not obvious. So yeah, I also think yeah, it'd be like there are a few differences from maybe the normal. But yeah, basically the idea is like, so this is an existential argument. Very simple. So similar ideas have been used in other proofs to show construct locally dense lattices. And it's easy to get a randomized version of this. So kind of the $1 million question, or okay, I guess there's no $1 million bounty on it, but just the key problem here, key question is whether you can show that something like this is true for some particular S. So fixed S.
Find such an S, you mean. Find such an S, right?
Yeah, oh, that's true. But I assume yeah, you're right. So find such an S sufficiently in like deterministic time. But like,
And that's
yeah,
it.
but maybe there's like a very simple description of such S. Yeah, you're right. But technically, yeah, generate such S's like in polynomial time as a function of Q.
Like, and that's it.
That's it.
The randomness.
Well, there's also this like map T I mentioned earlier, but kind of morally, this is the randomness. Yes. So it's like kind of, it seems kind of ridiculous and maddening. This is another one of these like hay and haystack kind of things. And I would say like conceivably, I believe, I don't know that Chris agrees with me on this, but I would bet that maybe any vector S in here will work. This is strong, please falsify that, but it's not 100% clear, but like we ran some experiments and like, these S's are very, very uniformly distributed across cosets. Okay, so I have 5 minutes left, or it started like yeah, slightly late. That's fine. So okay, so right. So just okay, how can we de-randomize this? So just based on, this is already kind of the discussion in the previous slide, just summarizing it. So we want to find some like explicit good center S. Yeah, such that there are many vectors in BQH in this coset of the code, or like say around that center. Just like kind of zooming out from pretty much everything I've said so far, you can just think of like this problem as being related to Reed-Solomon, wanting Reed-Solomon list decoding lower bounds, but not in the standard sense, but in terms of L1 or LP norms. Like think of that as a problem in isolation. It's an interesting question. So just one interesting thing that we showed with a nice assist from Swastik Kapardi was that sort of if we showed this as is, then it would imply improved like Reed-Solomon list decoding lower bounds actually in the standard sense. So you can interpret that in two ways. I'd like to say optimistically that it gives us like a way of thinking about improving Reed-Solomon list decoding lower bounds, but maybe you can also think of it as like a barrier. But actually there are kind of many ways to kind of get around this. It's just like a strong de-randomization. Like listed here. So kind of the main approach that we thought about, or we thought about a few, but one is based on discrete Fourier analysis and the Weybound. This is something that was used with great success for showing Reed-Solomon list decoding lower bounds for in the Hamming metric. So by originally by Cheng 1 and then by Guruswamy and Rudra. And also this is a key ingredient in showing deterministic hardness of the minimum distance problem. So like clearly this technique has worked in the past, but somehow it gets stuck just short of what we needed to do in our setting. I'm happy to talk about that more, but it's kind of, again, maddening. If the Weybound were slightly better, then that would be enough to show like for what we need, but it's not. I can explain, yeah.
But can you experimentally sort of test if you know the so the bound talks about the number of roots of
it's about bounding exponential sums, actually. Yeah. But yeah. So if we have actually maybe I only have like a minute left, but I'd love to say more. It's not hard to like summarize, but yeah, like maybe just take that offline. So right. Oh yeah. So in like another approach we thought of that I think we had fewer concrete ideas about, but also seemed promising was point counting using Gaussian maps. So, at least, yeah. Okay, so just to summarize in a nutshell what I talked about. So showing deterministic NP hardness of SVP is a beautiful question and unfortunately still open, but I hope that somebody in this room will solve this. Again, I really, I think that I'm biased, but I like our reduction. I really think it's the simplest one there is. And I think they're like interesting, concrete directions to pursue for de-randomizing it. So I mean, we thought about them a lot, but I think there's a lot more to think about there. And so just kind of jumping back to SVP more generally, I just want to state 4 things that I think are very interesting problems in the complexity of SVP. So the first is what I talked about, to prove deterministic NP hardness of SVP. The second could summarize as reducing number theoretic crypto to LWE. So efficiently reduce, factoring in discrete logs, say to n to the 10 approximate SVP. It's a really nice question. The third is to show some like fine grained hardness of SVP, but like strong fine grained hardness. So like say 2 to the n over 5 hardness of exact SVP under a standard complexity assumption. So like maybe something like SETH. And the last, which seems very challenging, is basically just to prove hardness of LWE or something, or under a standard complexity assumption. So like, as I said before, we don't expect to be able to show NP hardness of this problem, but kind of there's this beautiful area of fine grained complexity and other areas where we have a whole bunch of interesting other assumptions, which might be appropriate for showing some hardness. Okay, and then I'll just leave you with some parting words of wisdom for ITI. That's the end of my talk.
Time for a few questions, but in any case, we'll reconvene at 11. Questions?
results of Sloan and then this other Siegel and Roth.
Yeah,
For the lower bound on the Lade distance. I was having trouble finding the Sloan paper, so I'll have to.
it's in the book, Conway Sloan, like in the, just like in SPLAG, sphere packing lattices and groups. So they have it for like in another context also. It's for Craig lattices, not for solid construction lattices. They're closely related. So
Okay.
we originally adapted the proof we found there, and then but realized that people had thought of it. Look for Craig lattices and Conway Sloan.
And then the follow, so do you know, there like, sorry, are there like upper bounds on distance, right, in the late metric?
On the minimum distance, you mean, or?
Yeah.
Yeah, so I mean, in general, the 2K is tight. That was, I think, Noah or somebody asked that. Yeah. We have an example in our paper. It's the case. Yeah.
So so here's a possibly crazy approach to proving to randomize, following what Yuval was asking, right? So assume that gap CVP prime is Huck. Use that to construct a pseudorandom generator, like one that actually produces this sort of gadget lattice. Right? So now there are two possibilities. Either this is random enough to the reduction, in which case it will actually work, or it's not, in which case you break gap CVP prime. So in either case, you break gap CVP prime.
Wait, but you're thinking of some variant gap CVP prime instances again, or just
start from a hard problem, right?
Yeah. Okay. Yeah.
CVP prime in your case. We know hardness to randomness sort of you have very broadly, right?
I see. Yeah.
There are hard problems you can construct random generator.
Yeah. I see what you're saying.
Particular kind of random generator, one that will pull the particular reduction.
No, it's true.
So either it does pull the reduction, right, or it doesn't. In which case you break gap CVP prime.
Yeah. No, that's an interesting idea. So yeah.
Okay.
No, it's yeah.
It won't be pretty, but
No, it seems really cool.
To get like a generic DRG from.
no, you don't want one.
Like a very yeah.
You only want something that pulls sort of very simple tasks here, right? Yeah.
Also, did you guys look into, there is this paper of Silverfilm of the early 2000s that shows examples how to use Nissan's generator to randomize many randomized algorithms.
We didn't know. I mean, no is the short answer. I mean, we didn't look at go deep into the kind of generic de-randomization literature. Like we were trying to use techniques like Baybound and stuff that had worked specifically in this context before. But I mean, I think just both of your Bennett and Yuval's questions are really good. We should poke around more in the de-randomization literature. Yeah.
Well, this is a comment and maybe some brag, but also sort of a question because it might be relevant to part of what you're after. What I was doing was exploring how close you can get to the volume or Hamming bound in this context of the L1 norm or Hamming or Lee metric for packing from Z to the N. And I took an odd version of the Craig lattice. So I actually took the prime to be your prime Q to be twice the dimension plus 1. So that the residues only went from 1 to Q to the minus 1 over Q over 2. Okay. And so then, but then otherwise it was the same kernel that you set up. And what I showed is that for any minimum distance, as the dimension goes to infinity, the packing density doesn't go to 0, so that the volume bound is tight to within a constant factor.
And that was for L1, you said?
Yeah.
Interesting.
So this is it's an analogous property in the L1 metric.
Yeah.
To the known property for VCH codes.
Yeah.
That the volume bound is tight to within a constant factor as the size of the VCH code goes to infinity.
Yeah.
For any fixed minimum distance. Now the amount, the constant is dependent on the minimum distance. So it's further away as from the volume bound as the minimum distance goes up. That's what I was doing.
super interesting. I mean, it's, you know, we
So
did.
it seems, I'm bringing it up because it seems I don't understand this material very well, but it seems like it could be related to these locally dense properties that actually.
Yeah, so there's an interesting question about the connection between like density and local density also. So for like in lattice world, I guess like a lattice is dense if it's nearly tight with Minkowski's bound, and depending on how you parameterize these lattices, you do get like lattices that are essentially tight, like say I mean, it depends on how you parameterize it, but in some regimes tight up to a constant with Minkowski's bound. So, I might add like density does not seem to imply local density, at least in a way, so it's not just as easy as that.
Well, it seems, I mean, at least for your randomly chosen thing, I mean, like if you idealize it as a perfect packing, you know, an actual tiling where
Yeah.
everything is in a taxicab ball of radius k, then it just somehow does seem related.
Yeah, no, I mean, it's a very, yeah, I didn't see unfortunately didn't see your paper poking around about this.
You wouldn't, I mean, it's the paper is a kind of polyglot thing, so you wouldn't, but I could tell you.
Yeah, that'd be great.
Sounds good. Let's start back.